Hello, hello. Good morning. I would like to record a little lecture today that I use as my introduction lecture. It's a set of two lectures, and the first one is really to open up the concept of igneous rocks to very junior students, and hopefully this is useful because a lot of people ask me some questions that make me think that maybe I should make this lecture actually available for a wider audience. So let me share my screen, and we'll start here. And I trust you can see that now. So it's igneous petrology, an introduction, and I really like to start here with first slide. This lecture, as I said, is concerned with the petrology of igneous rocks. Igneous is from Greek fire, and therefore it is rocks formed by fire, if you will, so magmatic rocks, in other words. These, together with the sedimentary and metamorphic rocks, they make up the surface of the Earth. From our own experience, certainly in Sweden, we get a rather distorted picture because there the proportion of rocks is not the same as on a global level. Sweden has a lot of igneous rocks, mainly granites and granitoids, but also a lot of metamorphic rocks, gneisses, for example, and there is a different proportion than we see on a global level. So when we look at a global level, we have a large amount of ocean floor, and this is why I showed the ocean floor map on the previous slide, because ocean floor is almost exclusively, entirely made of basaltic rock, and so 2/3 of the Earth's surface is actually covered with basaltic rock, and that is, of course, an igneous rock. The continents, however, they are mainly made of more felsic rocks, and these are less dense. This is why the continents seem to be higher up. They float, if you will, in the mantle in a different way than the oceanic, basaltic, more dense rocks. And here, for example, in Sweden, we have a lot of these granitoid type rocks, and if they get eroded, they make sediments, of course. If they get then involved in an orogeny, they get under heat and pressure and they get metamorphosed, then they often become gneisses. So when we think about the Earth interior, however, much of the Earth is made of the Earth mantle, and then in the very interior, we have the Earth core. So here in the lower left, we have the Earth core, and that is made of metals that have segregated into the center of the Earth. And then we have this large area here that is the mantle, and the mantle is made of an igneous rock as well, and that is usually peridotite. It can have some other components like pyroxenite or pyroxene-rich rock, but peridotite is an olivine-rich rock that also contains pyroxene, but also some spinel and garnet. And here's a lovely specimen shown here. It's a garnet leucellite with a red garnets in olivine-rich peridotite. So when we take this little slice throughout the Earth, we'll see that the vast volume of the planet is actually made of the mantle. So the mantle is one of the largest reservoirs we have on Earth, and it's made of igneous rock. So in the beginning, there was an igneous rock, and most of the planet is indeed made of exactly that, igneous rocks. So in terms of volume, area, igneous rocks make up by far the largest part of not just the Earth crust, but the planet in general. So this is the very material our planet is made of. The Earth is around 4.6 billion years old, and more than 88% of its history are contained in these igneous and metamorphic rocks. The evolution of living things is actually a lot younger, and while it is important and while it concerns us every day, the Earth history is only spanning, in terms of life, is only spanning about 12%. So igneous rocks go back a lot further, and the oldest rocks that we have, or the oldest minerals we have, are actually igneous. They are zircon crystals that come from recycled igneous rocks that were worn down by erosion and are now found in sediments. So the really early Earth history that's contained in igneous rocks, we have a record of that, albeit a very complicated record, I must admit. So let's talk a little bit about different igneous rocks and how they form. As I said, igneous comes from Greek and it's meaning fire. So rocks that form from magma that come from inside the earth, magma that comes to the surface and then erupts, usually as lava or pyroclastic material. That is what we regard as igneous rocks. Well, there was a big controversy early on in the 17th century. There was two broad schools of belief, the Neptunists and the Plutonists. The Neptunists believe that igneous rocks like basalt would precipitate from ocean water, while the Plutonists believed that there was fire inside the earth that was bringing up these molten materials like magma. Here on the left, we have a drawing that goes back to the 1700s, and this is basalt columns, but the artist has actually put little tips, crystal tips on top, like you would see at quartz crystals, to imply that this was a crystallization from an aqueous solution. So there was an interpretation in there, because usually basalt columns don't have these crystal tips. On the right-hand side, we have Athanasius Kircher's view, and here we have fire coming out from the interior of the earth. He believed there was a fire burning inside the earth. Now, neither of them was perfectly right, of course, but the one on the right hand is probably a little closer to the truth than, for example, the one on the left hand. So today, of course, we know that there is lava coming out from hot interiors of the earth, and it comes out as molten rock. And we also know from actually very early experiments in the 1790s, Hall in Edinburgh, he was taking rock from the windsill, he was melting it and he was pouring it out and then inspecting it under the microscope and concluding it looks awfully similar to the original windsill. So therefore, he concluded the windsill must have been formed from quenched, i.e. rapidly cooled magma that was then near the surface and was chilled because of the temperature contrast. So this was the start of experimental petrology. So we know now how basalt forms. We also see this at volcanoes. We see it coming out. We see it flowing, like here, images from Hawaii, and we see it cooling, and we can take it to the lab afterwards and study it. So it's the product of cooling of lava. And if we have a lot of lava pouring out, we make these shield volcanoes, particularly if it's very runny lava. So volcanoes like Hawaii, they form these beautiful shields, but we also have some further out in the universe. Olympus Mons on Mars is a gigantic shield. There we have a single heat source and a single magma supply source, no plate tectonics, and therefore we're pouring out the lavas into a wide area, making these beautiful shields. The typical volcano that we see on the planet, or that we envisage to be the archetypical volcano, is actually what we call a stratovolcano or a composite volcano, where we have alternate layers of lava and usually ash and pyroclastics. Pyroclastic is broken by fire, and because the lavas are not spreading out, they're not super runny, they can be a little bit more viscous, meaning they don't flow so well, then you build up a steeper cone, and this is what we see in many places. So here is Vesuvius, for example, in an old drawing, but also Fujiyama and various other volcanoes. These are the typical type of the cone-shaped volcanoes. They are made of multi-layers and successive eruptive events, not single eruptive events, and they are building up over time. Now, forms of igneous rocks. Let's talk a little bit about the different types of igneous rocks. We have lava erupted from volcanoes. We touched on this, and this comes from molten rock, molten fluids, and they're hot and sticky. And if they erupt explosively, then, well, you need either very high gas content, or the magma needs to be more sticky, more viscous. And this led Katja and Maurice Kraft, two very eminent volcanologists, to distinguish between black and red volcanoes. Black volcanoes have low silica, the magma is very runny, whereas red volcanoes are more explosive. And often the fragmentation of the material in the explosive eruption phenomena gives rise to oxidation. Hence, these rocks or these volcanoes tend to be a little more red because they have larger surface areas for interaction in a hot state with the air. So they often have high silica content, and therefore we have these two different types, the black and the red volcanoes. On the left here we have the black ones, and here on the right we have the more red ones. So this would be Icelandic type, Hawaiian type, Strombolian, and Volcanian type. There can be some fire fountains in these types, not an issue, several tens to hundreds of meters even, but this is nothing compared to Vesuvian type, Plinian type, and Palean type. They form kilometer-high explosive columns with a lot of gas and ash entrained. So this is the ones I'd like to start with, the black types. So here we have different lava types. This is usually related to cooling, and if the lava runs very smoothly, if it flows very smoothly, we make pahoehoe lava, which I'm showing here in the lower left. And then if the lava cools, it gets quite blocky, then this will actually form a blocky lava here, shown on the right-hand side, where we have a blocky lava that travels actually over a pahoehoe lava. So pahoehoe lava has often these ropey textures. Imagine you have a hot chocolate, you get a skin on a hot chocolate, and if you blow against the skin, it starts to wrinkle up. So actually it wrinkles up perpendicular to the flow surface. So the ropey textures don't give the flow direction directly. You have to look at it in a 90-degree direction from the actual orientation of the wrinkles, and that gives you the compression direction, the flow direction. But here you get a good idea of how this works when you're looking at these pictures. And these lavas can, of course, flow rather rapidly, tens of kilometers per hour. So at La Palma in 2021, it was measured that they can travel at 30 kilometers per hour. This is a fast moped, so it gets actually quite fast, and it's not so easy to run away. And fixed property like this house here in Hawaii has, of course, well, no chance. So if that's in the way of a lava flow, then this is serious. However, for most parts, the effect on human life is limited, because people don't die usually from lava flows like this, because you can walk away. So then here we have lava lakes and lava tubes. So if lava flows into a depression and it cannot be drained, then you might get a lava lake. Or if lava cools over, if a flow cools over, forms a crust and continues flowing underneath, you actually get a lava tube or a lava tunnel. So here is the entrance to one of those lava tubes. This is on Hawaii, and there you can look inside and you see how it's crusting over. So there, hopefully you can see my cursor here. This is the crust, but because there's movement underneath, you actually break up that crust. Eventually it will crust over and the flow will continue inside. So here, these lava tubes can then drain out, as I said, and then you have these caves in the Canaries, for example, and also in Hawaii, spectacular for exploration, of course. So here we see a fissure eruption up there on Hawaii, and it's producing lava that's plunging into a lava lake. And as you can see from the fashion here, this is a few years old, and here is one of these lava lakes on Hawaii. And you see that this is now filled up and it's starting to cool. It's still liquid inside, but it's starting to cool very gently. And there you still have gas escaping from the cooling lava lake. So here you also have a lava lake where you see a little bit of an injection, and lava lakes are actually fascinating. So lava lakes like on Hawaii, on the Big Island, there you see all sorts of things. And in fact, some people claim you can see tectonics en miniature, and the surface of the lava lake, you have little transform faults when there's convection inside, pretty much like you see in the ocean crust, but you also have triple junctions. So some people say lava lake surfaces are a wonderful analog for plate tectonics. And you might even see subductions there. Sometimes the thicker, cooler crust is actually pushed underneath a little bit of younger crust, and there you actually have subduction phenomena. Like here's a subduction zone at mini subduction zone on top of a lava lake, and here you squeezing one surface under the other. So miniature plate tectonics in lava lakes, and the USGS has drilled lava lakes on Hawaii, and here the Alai lava lake, and this is depth in meters, and I think there is still remnant heat inside, so you can drill in there, and you can actually stand on it. Here's a small drill rig, and drill into the hot and liquid interior. So once lava lakes cool, then you actually get columns, cooling columns. They're very famous from the Giant's Causeway, for example. It's a cooled tholeiitic lava flow at the Giant's Causeway, and it makes these polygonal columns. So when lava cools, it cracks a little because it shrinks when it cools, and then it makes these columns. And another one here in El Hierro, in the Canary Islands, where you see the upper and lower parts of a lava flow that have formed these columns. Blocky lava is a little different. It moves a little different. It doesn't run quite so smoothly. It moves more like the chain of a caterpillar, and it rolls over, if you will. And this is often a misconception, because this one cannot be diverted by digging a channel, for example. This is much, much harder to stop. You need a wall, a barrier that stops it, and then you might have a chance, or it often runs over things, and this can lead to some confusion. So this is the more difficult lava to deal with when you have a civil protection situation, for example. So pyroclastic products, if there's enough gas and the lava cannot respond to expanding gas in a rapid way, often you shred the lava, and this is then called pyroclastic. Pyroclastic, broken by fire. So pyroclastic can be on small scale, like in fire fountains, like we see on Hawaii. Here, for example, it can be a few hundred meters tall, and then you get these droplets, and this is Pele's tears, Pele's hairs, for example, and small fragments like lapilli. But it can also be larger. You get these spindle-shaped bombs here, or this larger bomb here thrown out at, in this case, Krakatau, and bombs are usually bigger than this size here. And then if you have these volcanoes, they form cones, and there you have a pileup of these lapilli and ash layers together with lava. This one here is, for example, La Palma 1971 eruption, where you see a vent complex, and this was fire fountains that produced that in what we usually call a strombolian type. So this is the strombolian fire fountain, but I'd like to talk a few minutes also about the large Plinian eruptions here. And this is Mount St. Helens on the right-hand side, and this is a seriously Plinian type eruption, at least in terms of the column height, not in terms of the volume. Mount St. Helens was not that big in terms of volume. So this is the big eruptions, and there we have Merapi volcano and the pyroclastic flow coming down. These red volcanoes, they erupt explosively. The magma is very viscous. It cannot just flow. The gas wants to come out. The magma cannot respond in time. So the gas expansion will shred the magma into smaller particles, ash, lapilli, bombs, depending on the amount of energy available. So this is a drawing from Vesuvius, and there we have a beautiful eruption column. Eventually, the eruption column will spread out when a density equilibrium is reached high up in the atmosphere. But there you can also have lightning effects, and you have a lot of ash that will then rain out. I hope you can see my cursor, but in the left-hand image, these dark areas under the umbrella cloud, that is actually ash that's raining out. And it makes usually very thick deposits of, in this case, an ignimbrite and ash cloud deposits here on the right-hand side with threads of material. We call them fiamme, or little flames, and this is compacted material that was formerly bombs or vesicular bombs in the eruption column. The lower one is a block and ash flow, and this is from Merapi, and you see the large blocks, and there's a tree, and you can see the roots of a tree. There's a meter stick here for scale. There where my cursor in the lower right image, just below that tree, there's this red dotted area, and that's the meter stick. And this is in a pyroclastic flow that runs down the hill, and really it decapitates the trees and creates thick deposits there. So if you have a lot of ash, then the ash can of course spread, and at Mount St. Helens within a day the ash actually spread enormous distances. So here you get an idea, it can actually travel hundreds and potentially thousands of kilometers within a relatively short time span. So if you then move into the volcano, hip abyssal rocks, well, they are rocks that are half deep. Hip abyssal, abyss is the depth, and hip is kind of half. So the half deep rocks, and inside a volcano, we have, of course, conduits and pipes, and we have little sills and magma chambers, and that can be filled with lava. And there we have vents, plugs, dikes, sills. And here in the little sketch on top right, you have the main crater, you have small side vents, flank cones, and these are all fed. So inside a volcano, you get a lot of fractures that are filled with lava, as I'm showing here on the bottom right-hand side image. There is a little dike that is filled with a reddish rock. In this case it's called an aplite, very fine-grained felsic rock that you sometimes see in granitic terrains. So these dikes, they are actually fissures, and the fissures may then feed eruptions. So here is different ones that different types of subterranean igneous rock geometries. So we have dikes. In the US it's spelled with a with an I, and in the UK it's spelled with a Y. So here we have the US spelling dikes, and then sills is horizontal or flat-lying, conform to stratigraphy, igneous intrusions. A laccolith is the one that bulges up, a lopolith is going down. I always confused them as a student, so I gave myself this little helper. I said, well, if you're lucky, you're moving upwards in life. So the laccolith is the lucky one, and it moves up. So then plugs, they're often circular or elongate. And then we have cone sheets, an inverted cone. And if you have pressure coming from a point source, you're pushing things ahead, and you get cone sheets. Ring dikes are usually when you have something collapsing, a caldera or so, and this can also happen underground. Then it's called cauldron subsidence. And these two are related, ring dikes and cauldrons, and you often get them in larger silicic systems. So a few examples here. There's the North Star dike in the top left image. It's actually in Northern Ireland, and it happens to point exactly north. This is why it's called the North Star dike. The lower image is from the caldera wall at Krakatoa, and there we have a few dikes here as well, cutting through earlier deposits. And as I said, if you think about cone sheets and ring dikes, cone sheets require lifting, and ring dikes usually require a subsidence of a block, potentially the block even pressing into the magma reservoir and therefore squeezing things out. Often ring dikes have overall a bell jar shaped geometry, because otherwise you can't move them. Otherwise they actually get stuck. They will not go further. So there's a space problem if you have it any other way. So fissure eruptions is something that I wanted to talk about very briefly. They are very important. Often when we have dikes or fractures that are filled with magma or lava, then they can produce fissure eruptions, as we see on Hawaii, but also in Iceland. So here we have some Hawaiian scenarios. I showed this image before. There's a fissure that produces lava. This is the Meradali eruption here in the top right from 2022, and that was initially a fissure. Eventually several cones form along the fissure, and eventually one cone takes over and becomes the dominant cone. This is the Laki fissure in Iceland, which produced a large eruption in the 1700s, and there is an alignment of cones. So the initial fissure was then starting to build up several cone type edifices, at which the eruption continued from the initial fissure type. So plutonic rocks, when you look into the depth or in the bowels of a volcano, or if you strip away the top edifice of a volcano, then you may look inside. Older igneous terrains often have the magma chambers exposed, and there we see much coarser rocks, plutonic rocks, deep rocks, if you will. So we can only look at them in extinct volcanoes or where some special circumstances have allowed us to look into that, maybe some tectonic faulting. So in eroded mountains like in the Andes in Peru or Chile, it is possible to look into the guts of such a volcano. And here there is a little quarry in France. I love the little quarry in the Auvergne in Lantichy, and there you can actually see little intrusive rocks that are here. The quarry has produced a lot of aggregate material, fine-grained material for roadworks, for agriculture, but there's some intrusive rocks, and here you see in the top right where these more coarse areas are, that is actually intrusive material. So in the lower left, I'm showing a coarse-grained granitoid type rock, and in the lower right, you can see this area under the cone, under the vent, and this is supposedly the coarse-grained area that is the plutonic heart of the volcano. So the flanks and the top edifice is usually lavas and pyroclastics, but the plutonic core heart of the volcano is the former magma reservoirs. So this is where we want to look now, and here's a few impressions. You could have even giant growth, and the top left image is from the island of Bornholm, and then we have these giant feldspars. There's a Danish coin for scale. The Danes have little holes in their coins, and you get the idea. And then a few granitoid rocks from elsewhere in the bottom left and the top right. So these are often pretty high in silica, and these granitoids, they get stuck. If they're more mafic, if the silica content is lower, you usually get gabbros, and then they're made of olivine, pyroxene, and plagioclase, while these rocks here, they're often made of plagioclase, K-feldspar, a little bit of pyroxene, but also quartz and micas and amphiboles. So this is a quite confusing range of minerals, and let's try to make a little bit of sense into that. And this was something that people have started to work out already as early as Darwin. Darwin realized that minerals can segregate in lava, and later Norman Bowen, he was a pioneer in the 1920s, and he did experiments, and he created a little system that we can still use, broadly speaking, today. So since Bowen's work, we have an idea that if we have a low silica rock and that crystallizes and cools, then we make olivine, pyroxenes, orthopyroxene and clinopyroxene, but also plagioclase. If we have an andesitic rock, then we get usually plagioclase, CPX, and hornblende. A dacitic rock crystallizes K-spar, maybe the first quartz, biotite, and hornblende. And a rhyolite, that's a high silica rock, that crystallizes, for example, quartz, K-spar, and biotite. Now, we must realize that these can actually form not in isolation, but also in sequence. And to create a sequence of rocks, we need to change some things. And this is where Norman L. Bowen was very instrumental. So here you see him as a young man on the left and as a more mature researcher on the right, where he worked in Washington at the geophysical laboratories. And he did a lot of experiments, as I said, and he realized when magma cools, then you make certain olivine or certain crystals first, and olivine is usually the first to form in a natural low silica magma. And once you make this olivine and you isolate it from the reaction with the liquid, then you make other minerals. So here we have an experimental set depicted on the left. Initially, it's all completely liquid. And once we make olivine crystals, the liquid will change its composition because the olivine has formed. And eventually, the liquid has changed to a degree that it can no longer crystallize olivine. It will start to make another mineral, in this case, pyroxene. And once it crystallized a number of pyroxene crystals, the liquid has changed again. And it will actually start to crystallize, in this experiment at least, SiO2. It will start to crystallize quartz. In nature, the system is often more complicated, and I'll come back to this. It's a multi-component system, so we get multiple crystallizing mineral assemblages. We get olivine and the CPX and OPX suite and plagioclase early on. And if we make these minerals and we put them away, then the liquid has changed. The liquid becomes more silica rich. It becomes actually an andesite, and if that forms new crystals, then the liquid eventually becomes a dacite liquid, and eventually a rhyolite liquid by continuous removal of crystals. So initially olivine, pyroxene, amphibole, biotite, the ferromagnesian dark minerals form, and later plagioclase, K-feldspar, muscovite, and quartz dominate. Plagioclase crystallizes almost throughout, but K-feldspar, muscovite, and quartz come only very late, as I'm showing here with my cursor on the right-hand side in the lower part of the diagram. So note that the early minerals that crystallize, they form at high temperature, and they often make the mafic rocks. Well, the other ones, they are the low temperature sweet, and they are more silica and also aluminium and alkali rich, and they make the felsic rocks or the acidic rocks. And as we said earlier, they behave differently in the way they erupt. So here is a fundamental process that actually causes these different compositions, and it leads to very different eruption behavior. So the normal sequence in the basaltic magma is olivine first, then olivine and pyroxene, pyroxene, plag, pyroxene plus plag. The olivine stops at some point because the liquid can no longer make olivine. The magnesium is sufficiently low. Then you get hornblende. Hornblende is the first mineral with water. So that means water has become enriched in the residual melt. And then we have biotite. Biotite also contains water, plag, and K-feldspar, and eventually we have K-feldspar, quartz, and platinum biotite. So usually the temperature drops during that process, and the minerals may react with the liquid, and they may convert themselves. Some minerals do that, others not. Those that do that are usually the mafic minerals, and they are considered the discontinuous reaction series, where we have one mineral forming and it's continuously reacting with the liquid, and there we actually form a new mineral from the solution of one, or the dissolution, sorry. So the feldspar is the other opposite extreme, the feldspar series. It converts itself in a continuous process, and that means we form a high temperature plagioclase, for example, a calcium-rich one, and then we get to a sodium-rich one, but we don't have this continuous reaction, and there we form a difference here. So there we form a reaction series, and this reaction series is called Bowen's reaction series, with a discontinuous reaction series and a continuous one on the other side. The continuous creates successive compositions of feldspar. The discontinuous creates successive minerals. So this is why it's discontinuous, the other one is continuous. This sequence is shown graphically in Bowen's reaction series, and here is a representation of this. We have basalt andesite to rhyolite on the left, and here's the discontinuous and continuous series. The discontinuous is the mafic minerals, olivine, pyroxene, amphibole, biotite, and the continuous is the plagioclase, which usually starts as calcium-rich plagioclase, which we call bitonite, labradorite, andesine, oligoclase, and albite, until we get very sodium-rich plagioclase. And just at the very end, we get potassium feldspar, muscovite, the white mica, but also quartz, and this is at relatively low temperature. So having established that igneous rocks form by sequential crystallization of a succession of different minerals that appear on cooling, then we can actually make some really good predictions. If magma is contained in a closed chamber, and we don't add anything, or we don't take anything away, then the final product will actually have the same bulk composition than the initial product, even though it crystallized. So in order to make different lavas that erupt at the surface, we need to actually take something away. So in the image here at the bottom, I'm showing equilibrium crystallization. We have a basalt magma here on the left, and if we just crystallize this into olivine and pyroxene, for example, and quench the liquid in between, then we might have a plutonic rock, but the composition is very similar, of course. Actually, it should be identical. So in order to create this new lava, we must separate the crystals and the liquid. So, and this is what Bowen calls fractional crystallization. Imagine we have a basalt magma here in the diagram on the bottom right, and we separate the liquid and say the crystals are raining to the floor because usually they should be more dense. Then we create a cumulate rock, a plutonic rock. That is a peridotite in this case with loads of olivine and lesser pyroxene. And we have a residual liquid, and the liquid is usually a basaltic andesite or so. And if that liquid moves up through the volcano, starts to form its own magma chamber, then it can actually crystallize again, and maybe it crystallizes a slightly different mineral assemblage. But if we separate that again, we make yet again a new liquid. So the new residual liquid could be, for example, an andesite, and the cumulate is also a little more evolved. It's then a gabbro. So if the liquid is to evolve to produce more felsic magmas, the minerals must be removed. We must fractionate the crystallized products from the liquid. So, and if we do this, we call this, as I said, fractional crystallization. Fractionation works by removing early minerals and not letting them react anymore. And this is why we get cumulates in the bottom of magma chambers. And this image here on the top right, it shows crystals that are raining down. In reality, it's probably a little more complicated because there's also convection in the magma chamber. We'll discuss this some other time, but in principle, the denser products end up at the bottom. So this is an example from my university teacher. This is salt solutions in analog. So this is from Colin Donaldson. So if you imagine you have a beaker of salt water and it's warm and the salt is in solution, then you can look at this as an analog to magma. So if you cool this, then you'll start to actually have crystallization, because the cooler the water, the less salt it can contain. And then eventually when it's cold, you have salt crystals that pile up. And if you have evaporation, that helps, of course. So, and that means that the change in composition is pretty obvious because the liquid will actually evolve in a different way. Then the crystals that are formed, the crystals are effectively natrium chloride. They are salt crystals, and the liquid is actually less saline. So another example that some people have used, and that is if you put a bottle of wine in the freezer. If you put a bottle of wine in the freezer, you will make water crystals, ice crystals, and the liquid that is remaining is very highly concentrated in alcohol. It's well, a very cheap way of making stronger spirits if you want, and it's apparently, yeah, not very tasty. I've never tried it myself, but you can see that the crystallization separates water and alcohol and therefore creates an enriched liquid. In our magma comparison, it would be high silica liquid that's remaining and a more mafic crystal residue. You separate them. So comparison with magma, here we have a parental magma, a basaltic magma. For example, we isolate olivine and plagioclase and we make a daughter magma, e.g. an andesite. We isolate then new crystals, pyroxene, plagioclase, maybe hornblende, and then we make another daughter magma, a rhyolite. Now, humans love to have things in little stages, and if you want, you can make this in very minute, small stages. So here's one again from Colin Donaldson. You have a daughter magma that is 56 after a basalt from which you separated a gabbro assemblage. The next daughter magma is a little higher in silica, maybe another andesite, and again, you made a diorite residue, a cumulate. And then the next daughter magma, maybe again a little higher in silica, maybe a dacite, and you have made a granite diorite residual cumulate. And then you make another daughter magma. The residual liquid now is a rhyolite and would have very high silica, while the material in the plutonic rocks would be a granite diorite or even a granite, and eventually you can make a rhyolite. In nature, of course, it doesn't happen in steps. It's a more gradual process. Nature doesn't say, oh, now we have another this or that. It's more of a sequence of events. Now, Do we have some evidence for this happening in reality? Well, one line of evidence is that we have quite frequently sown feldspars, and there may be complications because of magma replenishments, but we do sometimes find anorthite-rich cores, calcium-rich cores that go all the way to albite-rich rims. If you look here at the feldspar triangle, this is the calcite corner in the lower right, and the anorthite corner. And if you have basalt, andesite, dacite, the plagioclase would go more and more sodium rich, that's the albite, and eventually it goes more alkali rich, and therefore more orthoclase component comes in. So we're going from calcium to sodium to potassium dominated, and this is what we frequently find. So a healthy feldspar that hasn't been interfered with during crystallization would actually show a zoning in that direction, and that is very good evidence for this process actually being at work in many magma chambers. Another one is layered intrusions, and layered intrusions, for example, like the Skaergård, but here also the Rom or the Bushveld. There we have cumulate piles. So the concept of crystals raining out, particularly dense crystals, is quite a possibility. And here on Rom in Scotland, we have these successive layers of olivine-rich material followed by feldspar-rich material, and a new layer then brings again olivine-rich material. It's believed to be a sequence of multiple magma injections, which each produced a new system or a new event of crystallization. So this is part of the British and Irish tertiary igneous province. Rom is the second from the top, the red star, the second from the top, just on the sky, in the bottom right-hand image. And this is the Isle of Rom. It's a major plutonic suite, the heart of a former volcano. The volcano is largely gone. There's nothing left, but there we have this major layered suite. It sits on a fault, so it's actually pretty analogous to what we see right now under Iceland, where we have a lot of fractures that give rise to these volcanic eruptions on the Reykjanes Peninsula. And in cross-section, it looks like this. We have repeated intrusive pulses of lava or magma, sorry, it's underground, into a magma reservoir. And these are usually basaltic, we assume, and they will start to crystallize olivine, and the olivine will rain out, and later there will be more feldspar. And if you look at these units, these individual layers, this is going back to the work by Brown in the 1950s. We have a lot of olivine in this major unit, unit 10, which is kind of the type unit. And then the olivine is reduced. You see the olivine here in this stippled line on the right-hand side. And then the pyroxene is wobbling around, but the plagioclase is rather low in the lower part of the unit, and it actually increases dramatically towards the top. So the dense early crystallized materials would settle out and segregate at the bottom, making an olivine-rich cumulate that eventually grades into a plagioclase-rich cumulate. The height of this unit is about 300 feet. That's about 100 meters. And I would like to move on to the next evidences, and that is lava lakes. Lava lakes are a beautiful natural laboratory, and the USGS has drilled into Hawaiian lava lakes, and they are a bit like a magma chamber that's solidifying. First of all, it solidifies from the outside because cooling is most efficient on the outside, of course. So we have a liquid interior, and here we have the concept of a lava lake with a remnant heat inside while the outer parts are cold. So you can actually stand on top there, and you can, well, drill into the gooey bit in the middle, if you will. And of course, people have done this, and here we see this is the interior. It's rather liquid. We have some larger crystals, but a lot of glass, because now when we extract that, it's quenched. And then depending on the temperature difference, we see more and more crystals. The cooler it gets, the more crystals we have. And if you take the glass in between the larger crystals, then you'll actually find that the glass, although the bulk rock is basaltic, the glass is quite high silica, approaching dacitic and rhyolitic compositions. So this has given rise to a lot of interesting research where we can actually see the changes in the lava lakes, and there is more glass in the middle, because this is the part here in the diagram where we still have the gooey interior, if you will. And this glass is still pretty high magnesium and low silica, but in those areas where we had a lot of crystallization, for example, in the crustal areas up here and also at the bottom where it cools as well, there the remaining glass has actually evolved. It's more silica rich, and that's also a form of fractional crystallization in this case. And then evidence 4 is, of course, the overall suite that we often observe in volcanic sequences. And there we often see it goes from mafic, from low silica, to more felsic or acidic compositions. And this has been shown in Harker diagrams by Alfred Harker, one of the pioneers of igneous petrology. And he came up with this idea to plot against silica or magnesium. And this allows us to see changes that are caused by the removal and crystallization of minerals. So magnesium, for example, if you crystallize olivine, the magnesium in the remaining magma or liquid will go down, and eventually we stop crystallizing olivine and other crystals will form like pyroxene that need less magnesium. Calcium, for example, well, olivine doesn't take up super high amounts of calcium, so you don't see a lot of changes when you crystallize olivine, but as soon as pyroxene and plagioclase start to crystallize, you see dramatic changes because these minerals take up calcium. Olivine takes up a little bit of iron, so there's small changes, but as soon as you start to crystallize iron titanium oxides and you remove them, then you get a big kink in the geochemical evolution relative to the change in silica. So different primary liquids will produce different sequences, of course, but overall there is a change, a systematic change. And here we have different suites of minerals forming, and they cause different changes in the resulting geochemical trends. And this magma evolution, the chemical evolution of magma, is shown here. So aluminium may even get enriched initially when only olivine is growing, because aluminium goes into plagioclase. But as soon as the other minerals like plagioclase are starting to crystallize, we're going down. Phosphorus is often going up until apatite crystallizes. Sodium is generally increased. Even with feldspar crystallization, we can't take up quite so much. Silica is always is also increased, and this is why here at the end we're making the quartz. Calcium rises again like aluminium a little bit until plagioclase comes in, and then it's reduced. Iron is often enriched here until a lot of iron titanium oxides grow, and titanium is affected by the iron titanium oxides as well. So these are the magmatic trends that we see, and again, they can be linked to minerals. So crystallization of minerals, sequential crystallization, and also fractional crystallization is a key process here. This is the TAS diagram, the total alkali. Here's the total alkali, sodium oxide and potassium oxide versus silica. And these are agreed rock names. And usually we're starting somewhere in the lower left of the diagram and we're moving towards the lower right. So we can have different variations along the base here between, say, picrite and nephelinite, depending on where exactly you are in the world. But the evolution of fractional crystallization always brings you to the right towards higher silica composition. So a basalt may then yield a daughter liquid that is, say, a trachyte andesite, and that in turn may yield a daughter liquid that is a rhyolite. So, and if we go to natural volcanic systems, like here, some tertiary volcanoes, Mull and Skye in Scotland, again, I mentioned the province earlier. There we see that we often start here in the basalt area, and then we have these evolutionary trends. The Skye main lava series, the red cloud here that is given in the diagram, it starts with a big bulgy bit in the basalt area, and it moves towards the right. And that is where fractionation has occurred. Usually 100 parts basalt will yield only about 5 to 10 parts rhyolite, so it's not uncommon that we have a lot of basalt and volumetrically lesser amounts of rhyolite. So let's summarize here. Magmas have family kinship with each other because they are often related to a single parent. And once the parent cools, sequential crystallization of initially mafic and then felsic mineral sets in. Crystal formation from these magmas involves the mafic minerals, olivine, pyroxene, amphibole, biotite, but then the felsic ones are calcium-rich plagioclase and or feldspar, and then eventually sodium feldspar, and then also quartz. If crystals are removed, the liquid will be depleted in those components, and therefore it will change its chemical composition, and fractional composition can produce new daughter magmas that then give rise to, again, new mineral assemblages. And this can explain a whole family relationship of chemical compositions at a single volcano. This process can explain the large variety of igneous rocks we see at individual volcanoes. Volcanoes that mature tend to have more felsic materials with time, and there we see these variations, and we can now explain them. So now the big question that results from this is where do the parental magma comes from? And that is another lecture where we have to think about how we melt magma in the mantle, how we produce it by melting the mantle, and how we produce mantle rock to produce magma that then rises up to actually differentiate, to fractionate, and make these new and varied compositions. But that's for the next session, and I'd like to say thank you very much so far, and all the very best. Okay, bye-bye. See you then.